Hello everyone. Today I'm going to talk about joint work with Naya Gerolamo, titled "A Discrete Morse Perspective on Knot Projections and a Generalized Clock Theorem." So basically, what we're going to do is we're going to generalize Kauffman's clock theorem in a few different directions, and we're going to explore some relations between discrete Morse matchings, so something coming from graph theory, and knot projections. So let me start by giving the main definition we're going to use throughout. This is the definition of mark projections and Kauffman states on them. So a mark projection is just a knot diagram basically. And by the way, I'm going to talk only about knots today and not links. So a mark projection is just a knot diagram in which we forget about the over and under information. So basically it's just a four-valent graph on the two-sphere. And the marking is this arc A. So an arc is just a segment going from a crossing to another crossing and not meeting any other crossings in between. This A here is called the marking or the forbidden arc. So the forbidden arc, you can see here, this is marked with this asterisk, is, uniquely identifies two regions in the complement of this projection on, let's say, the two-sphere. So in this case here, the two regions in the complement would be this one and the external one. So Kauffman state on such an object is just a bijection between crossings and the regions that are adjacent to each crossings and are not forbidden. So there are at most, of course, four regions around each crossing, and at most four of these might not be forbidden. We denote the whole set of Kauffman states on a given fixed mark projection in this way with this xdA. Okay, so another thing we can do given projection is to construct the black and white graphs. These are common graphs associated to knots. So the main idea is to start with a checkerboard coloring of the complement of the knot, so of the regions S2 is divided in by the knot projection. And by checkerboard, I just mean that at each crossing in the diagram, we want the opposite faces to be of the same color. In this case, we choose as colors black and white. And you can see here the black graph is the graph whose vertices are the black regions in this specific coloring of this five crossing diagram, and edges are given by crossings, while the white graph is just the same thing, just replacing the black regions with white ones. And note that again here the edges in this graph, in this white graph, are again given by crossings. So it's really easy to see that these two graphs are in fact plane duals, meaning that the vertices of one correspond to the faces of the other and vice versa, while there is a bijection between the edges. So basically for each edge, let's say in the black graph, you have a unique one which is called the dual one in the dual graph. Okay, now we can do a few things with Kauffman states. The first one is, Kauffman states provide us with these Jordan resolutions. So this, as suggested in the top left figure, is just it's just an embedded cycle on the two-sphere obtained by resolving the diagram in this way for each component of the Kauffman state. By the way, I forgot to say that here, for example, you can see the three possible Kauffman states on this marked projection of the trefoil with the same, of course, marking here. And we denote the bijection between the crossings and regions by placing these little dots near the crossings. And the fact that this is a bijection, that the Kauffman states are a bijection, mean that, imply in particular that any region must contain at most one of these little dots. It might contain none if the region is forbidden, for example. Okay, with this at hand, we see that for each if for each component of a given Kauffman state we resolve the diagram as shown here, we get just a circle embedded in the sphere, which is called the Jordan resolution associated to that given Kauffman state. Also, we can create a new graph starting from Kauffman states whose vertices are just Kauffman states on a given marked projections, and edges are given by the following construction. So if we have like a Kauffman state on a marked projection that locally looks like this, we can just switch the position of these two sort of adjacent components and obtain another Kauffman state. This is called a clock move. And in particular, if we go from left to right, this is a clockwise clock move. So the clock graph has as vertices Kauffman states and as edges these clock moves. So we can see here in this 4 crossing projection of some knot, we can choose, let's say, if we choose any of these red arcs here in the projection as forbidden arcs, then we obtain this clock graph for this projection. While instead, if we choose any of the black ones, we get this one here. So it's clear that the actual clock graph depends a lot by the choice of the forbidden arc and not only on the diagram we are considering. So with this at hand, we can state Kauffman's clock theorem, which is a result from the early 80s. And it's a 2-part theorem. We're going to see a generalized version of this, of both these parts in different parts of the talk. So let's start with the first one. There is a bijection between spanning trees in the black graph, and I'll say in a minute just what I mean. On the black graph of a given marked projection, and Kauffman states on the same marked projection, and Jordan resolutions of this diagram. So what is a tree? A tree is just a subgraph, in this case of the black graph, which is contractible, has no cycles. Spanning just means that all the vertices inside the black graph are part of at least one of the edges in the tree. So let's see here with a concrete example what we mean by this. What is the content of this theorem? So let's start from our marked projection. You can see here this is the forbidden arc, indicated by this asterisk, and we have a Kauffman state on this. So for each crossing, we are choosing one of the at most four possible regions around it. In such a way that the association is a bijection. Now we can consider the, let's see, here we have the black graph for this choice of coloring superimposed with the diagram, and also we have the white graph here. So what we can do is we can consider the two vertices of the black and white graphs respectively as a sort of privileged vertices, and I'll say in just a minute what that entails. So now to pass from a Kauffman state in red here to this pair of spanning trees, what we do is for each edge in the black graph, which corresponds to a crossing with a component of a Kauffman state in a black region, we add that edge to this, in this case, yellow subgraph. And if we do this for the black graph, there are exactly two of these components, one here and one here, and we get this yellow tree, which has one vertex in the forbidden region. We can play the same game for these two components in the white graph, and we obtain this other tree here, which instead is based in the external region, which is the forbidden one. So it's not hard to see that, in fact, starting from a Kauffman state, what we get, for example, in the black graph is always a tree, and it's always spanning. And also it's a classical result that in this case, if we have a graph and it's dual, in this case black and white graphs, then a spanning tree in one uniquely determines a spanning tree in the other, just by considering all the edges that are not part of the tree in the original graph. So basically this amounts to say that this yellow subgraph here, this yellow tree, uniquely determines this blue tree. Now, if we want to go in the opposite direction, let's say we are given these two trees in a graph and it's dual, we want to find out what is the Kauffman state. To do this, we root this tree in the vertices and we orient them away from the root, as shown here in the figure. And basically the components of the Kauffman state can be recovered by looking at the, let's say by placing a dot near the target of each of these oriented edges. Now, a nice thing to observe, I won't talk about this last part regarding general resolutions. The nice thing that we'll need though in what follows is that the Jordan resolution always provides us with neighborhoods of the black and white subgraphs induced by a given Kauffman state. As you can see here, if we resolve the diagram as shown in the upper left picture here, we get this circle here embedded in S2, which gives us, of course, it's a neighborhood of both the black and white subgraphs. Okay, let me go on with another classical construction. Oh, sorry, I forgot to mention the second part of the clock theorem. This is that the clock graph, so this graph constructed from Kauffman states and clock moves, is in fact connected, which again implies that basically if we have a fixed mark projection, we can get from any Kauffman state to any other just by performing a finite number of these local clock moves. Now, another classical construction in knot theory, if we have a plane graph G, we will denote by gamma of G what is usually known as its Tait graph. This is just the superimposition of G with its dual. So vertices in this Tait graph come into three kinds. Those coming from the original graph G, those coming from G star, in this case black and white here, and also we have this whole bunch that is given by the unique intersection between dual edges. Of course, if you start from a given knot projection, let's say marked, then you obtain its black and white graph, and the Tait graph is just a superimposition of these two. And of course, these kind of edges, these kind of vertices here are just given by crossings in the original diagram. Here you see we have this again the same forbidden arc, which uniquely determines this this region and the external one as forbidden, and these are the circled in red vertices in the figure here. What we can also do is we can remove these forbidden regions and obtain what is called the reduced Tait graph, which is shown here on the right. So Tait graphs have a few interesting properties. So first of all, as I said, they are tripartite. So all the edges in a Tait graph connect a crossing and either a black or a white region. Moreover, the complement of a Tait graph is always formed by square faces, as you can see here. All the faces in the complement of this graph are squares topologically and are made as follows. So on two opposite vertices of the square you have crossings, and on the two other opposite sides you have one black and one white region. And this is for all the squares. Of course, if we consider instead the reduced Tait, this is no longer true. You can see here, for example, the external region has eight edges. And yeah, as I was saying, if we start from a given knot diagram, we can define its Tait graph as being the Tait graph associated to its black graph. Now, let me also give this apparently disconnected definition. A matching on a graph, G, not necessarily planar, even though the examples I'm showing here are planar, is just a subset of its edges consisting of edges which are disjoint, so no vertices in common. And the first example here on the left is a bipartite graph. All the vertices are either white and black, and all black are connected only to white and vice versa. And the red edges are meant to represent the matching. So these are the edges that belong to the matching. And we say that this one on the left is a perfect matching, since it's also spanning. All vertices are part of exactly one of the edges in the matching. On the right instead, we have a non-maximal and non-perfect matching on this other graph. And yeah, this would become both perfect and spanning if we added this edge here to the matching. Okay, there is a construction due to Kenyon-Propp-Wilson from the late 90s, which is, as we'll see, strictly related to Kauffman's clock theorem, or at least part of it. So the starting point for this theorem is a plane graph G with a choice of a vertex in the graph G and a vertex in the dual. So basically this amounts to the choice of a vertex and a region in the complement of G. If these two are adjacent, meaning that, if we are looking this through the lens of knot projections, this would just mean that G would be the black graph of some knot projection, and so V would be a black region, and F would be a white region, and adjacent just would mean adjacent as regions. If we adopt instead this more abstract point of view of just a plane graph, then adjacent just means that they are on opposite faces of a square face of the Tait graph of G. Okay, so if we have this adjacency condition, then there is a bijective map from the set of trees of the graph G into the set of perfect matchings on the Tait graph, reduced in the sense that we removed both the vertex corresponding to V and the vertex corresponding to F. If instead these two vertices we chose at the beginning are not adjacent, then this map is only an injection. And we'll see in a few slides that we will actually characterize the image of this map independently of the position of these two regions in terms of discrete Morse matchings. So I'll show in just a second that there is a bijection between perfect matchings and perfect matchings on a given reduced Tait graph for a marked projection, and Kauffman states on the same marked diagram. Granted that we have this bijection, then this map, which is also called sometimes KPW correspondence, actually coincides with the first part of Kauffman's clock theorem, namely that there is a bijection between Kauffman states and the set of trees inside the black graph for a given knot diagram. And for the first part of this remark, it's just pretty easy. So we have here, this is the bijection between Kauffman states and perfect matchings on the Tait graph. We start here on the left with a marked projection. Again, this is the forbidden arc, and a Kauffman state in blue. And to this we can associate on the reduced Tait graph, where these two basically vertices are removed, the one marked in red. You can see that by just adding to the matching each half edge, which is determined by the pair region and crossing, like this, for each component of a Kauffman state, we obtain a perfect matching on this on the Tait graph. Okay. Let me apparently change slightly subject for a moment. And in what follows, for us, X is going to be either a simplicial or a regular cellular complex. And I'll blur a bit the distinction between the two in what follows, since the theory is precisely the same. So, given such an X, its phase poset, f of X, is just a directed graph whose vertices are either the simplices or the cells of X, and the edges are given by phase inclusions and are oriented towards decreasing dimension. So you can see here an example with the 2 simplex. Here it's phase poset. We have one vertex corresponding to the whole 2 simplex, then 3 vertices corresponding to the 3 edges, and 3 other vertices corresponding to the actual vertices of this simplicial complex. Oops. And here we have a construction which is due to Cohen, which is crucial to everything we're going to do from now on. Given a diagram D, or better a projection D, we can construct a cellular structure on the 2 sphere, which we call psi of D, whose 0 cells are given by the vertices of the black graph. 1 cells are in bijection with the crossings in the diagram, and 2 cells are in bijection with the white regions in the complement of the projection. So the crucial remark here is that the phase poset, so there's a directed graph here of this decomposition induced from a given knot projection, coincides precisely with the Tait graph for D. Of course, the Tait graph does not come with an orientation naturally, so we can just give a canonical one, which is orienting from well, in such a way that this is consistent with the with being a phase poset of this specific cellular structure. So we orient from white to crossings and from crossings to black regions. And here another thing to note is that well, for the easiest way to see this is to use Euler characteristic, is that any perfect matching on any Tait graph of a given knot diagram must leave out at least two vertices, which will correspond to 2 regions in the complement of D. And well, either you try to prove this directly, or we'll see in just a moment, and this is just using Euler characteristic, or we'll see in just a moment that there is a connection indeed between such matchings on the Tait graph, and a sort of discrete version of Morse functions, and the fact that that at least 2 regions have to be left out will correspond to the fact that regions that are left out by a matching will be called critical and will correspond to this sort of discrete version of critical points for a smooth discrete function on the 2 sphere, which of course must have at least 1 minima and 1 maxima. So this is where these 2 come from. But I'll be more precise in just a second. Oops. So if we have a matching on this specific graph, which is the phase graph of a cellular simplicial complex X, then we can play the following game. We can invert all the arrows that belong, all the edges, well, we can invert the orientation of all the edges that belong to the matching. If this does not create any oriented loop inside the phase poset, then we say that M is a cyclic, or also that M is a discrete Morse matching on X. On the other hand, if after reversing the orientation of the edges of a matching, we do obtain some oriented cycle in the phase poset, we say that these cycles are supported by the matching M. And of course, in this case, M is not a discrete Morse matching. We see here an example again with the two simplex. These red arrows are meant to show a pairing between these vertices and the respective edges here, as well as between this edge and the whole two simplex. And you can see here we have the phase poset, and again here we can we have colored in red the edges corresponding to this matching here and reversed their orientation. And you can check that indeed in this case this is a discrete Morse matching, since there are no oriented loop in this amended phase poset. Of course, discrete Morse matchings, or better, discrete Morse functions were introduced by Foreman around a bit more than 20 years ago, and they are one of the possible ways of porting Morse functions from the smooth world to the discrete one. And in fact, a discrete Morse matching can be thought of as being the sort of gradient flow of a given discrete Morse function on the simplicial complex we started with. Okay. If we have projection D of a knot, we can generalize slightly the definition of Kauffman states to obtain these partial Kauffman states. So a partial Kauffman state is just an injection from a subset of crossings to their at most 4 incident regions. So here we have generalized in 2 directions basically. First of all, we do not require that all crossings are matched. They do not necessarily have to have one of the components around them. And also we are not prescribing any specific forbidden regions. Particular, well, we've seen before that there must be at least 2 regions that are not paired by such by any matching, but these need not be adjacent necessarily. And we'll see an example in just a second, but and we'll just denote by this x tilde of D the set of partial Kauffman states on a given projection D. Also, I need to mention that these partial Kauffman states are not related at all with the partial Kauffman states by Otto and Szabo related to their border algebras to compute non-full homology. But the contest should make this quite clear nonetheless. Okay, we have these 2 examples here. Again, we have on the left a partial Kauffman state, and you can see that the 2 regions that do not contain any of these components in red are not adjacent. And again, here you can see in red, these are the half edges in the Tait graph that correspond to this partial Kauffman state. And again, here the 2 vertices that are circled in blue correspond to these forbidden regions in quotes, since these are not determined by a forbidden arc. Also on the left we have something similar. We have the same 2 forbidden regions here. However, if you actually put in the orientation inside this Tait graph, you can see that here we have 2 oriented cycles, which are this sort of length 4 cycles around each of the 2 forbidden regions. Okay, so just as before, we have a bijection between matchings on a Tait graph and partial Kauffman states. So before we had a bijection between perfect matchings on a given marked projection on its Tait graph and Kauffman states. Here we are just slightly generalizing this. And let's see another set of examples. Again, just as before, if we have a partial Kauffman state, we can consider its Jordan resolution. So we resolve for each of the components of the partial Kauffman state. We open the diagram in the direction the dot is going to. So the main difference here is that, like in this case, we do not get an embedded circle. We get something which has a double point here. Or in this other case, we actually get more than one connected component. So a few things can go wrong with respect to the previous case of Jordan resolutions. Also, we'll denote in this way the number of cycles on S2 that we get. Let's say of connected components. So this on the left would count as 1. However, as before, we can consider subgraphs in the black and white graphs respectively that are induced by a given partial Kauffman state. And in this case, we see for this example here on the left and on the right, here we see that, for example, the induced subgraph of the black graph here is not connected, so it's not a tree as before. And on the right, instead, you can see that even worse, this blue subgraph, which is the subgraph of the white graph induced by the partial Kauffman state here above, is not even simply connected. So it has this loop here. However, just as before, the Jordan resolutions, so this oriented, disjoint union of immersed cycles on S2 gives us again a neighborhood of these two subgraphs of the white and black respectively, just as before. Only in this case, it could have more than one connected component and be a bit weird, as in this case, where a single vertex is contained in this little portion here. Okay, so we will say that a loop is supported by some partial Kauffman state, or equivalently some matching on the Tait graph of a given projection, is monochromatic if all of the vertices in this loop are either all black and all crossings or all white and all crossings. So we have an example here with these 5 components of a partial Kauffman states that are circling around this white region, and here we have the same thing seen at the level of the Tait graph. And here we have, after changing the orientation of all these red edges that are given by the matching induced by this partial Kauffman state, we see that we have a length 10 oriented cycle, again circling around this isolated white component, white vertex. Okay, so the first result here is that if we are looking for discrete Morse matchings, this is the only thing that can go wrong. So a partial Kauffman state on the Tait graph of a given projection will induce a discrete Morse matching on this simplicial structure on the two-sphere, if and only if it does not support any of these monochromatic loops. And we can say even a bit more. So if we assume that X is a maximal partial Kauffman state on D, then if the two unpaired regions, or vertices, if you're looking at the Tait graph, are adjacent or opposite sides of a square, then X will induce a perfect discrete Morse matching on the two-sphere, on this Xi of T. So basically, all Kauffman states give us Kauffman states, meaning determined by marked projection give us discrete Morse matchings on the nodes. Okay, before we had the bijection between Kauffman states and trees as contained in the first part of Kauffman's clock theorem. We wish to generalize a bit that construction, so let me give a few definitions in that direction. So a partial Kauffman state is said to be admissible if it does not match at least one vertex of each color. So we know from before that all partial Kauffman states must leave unmatched at least two regions. However, it can happen that these two regions are of the same color, for example. And in that case, the partial Kauffman state wouldn't be admissible. We want at least two, and this is granted, and one white and one black. Also, as no, I didn't mention it before. A forest inside a graph G is just a disjoint union of trees. And if we are talking about plane graphs, two forests, one in the plane graph and one in its dual, are said to be orthogonal if basically their edges do not overlap. If we have one edge belonging to a forest in G, we cannot have the dual edge in the forest in G star. And yeah, this is the result. There is a bijection between discrete Morse matchings on psi of D, which are induced by admissible partial Kauffman states, and rooted and orthogonal spanning forest in both the black and white graphs associated to D. And again here, spanning just means, as before, all vertices or part in G and in G star respectively are part of the two forests. Rooted just means that again there is a preferential vertex in each of the connected components of each of these forests, and this could be, as we saw before, for example, even isolated components made only by a vertex. And in fact, this is indeed an extension of the clock theorem, since if we are talking about admissible and maximal partial Kauffman states, then this reduces to bijection between perfect discrete Morse matchings and rooted orthogonal spanning trees, which is basically a restatement of the first part of Kauffman's clock theorem. Even more, using this, we can give a sort of really simple criteria in terms of Jordan resolutions for when a given partial Kauffman state admissible induces a discrete Morse matching on psi of D on the two sphere. This happens if and only if the Jordan resolution is connected. It might be immersed, so not embedded, you might have double points, but if it's a unique component, then the partial Kauffman state you started with is indeed a discrete Morse matching, which is kind of handy, since looking at the Jordan resolution is quite easy, it's really quick, while in general checking on the phase poset whether a given partial Kauffman states induces something cyclic is slightly less user-friendly, let's say. In fact, using this last result, we can actually also count the number of first perfect and then general discrete Morse matchings that we can obtain on from a given knot projection. I should also say that in general counting discrete Morse matchings or matchings is not easy, so there are not many classes of graphs or simplicial complexes where we can actually easily count them. This is sort of an exception for plane graphs arising from knot projections. Particular, given such a knot projection or a diagram of a knot K, we can consider the Laplacian matrix of its black graph. This is just a matrix that can be combinatorially sort of built from the given graph. I won't go into the definition, but it's really easy. And also, this Laplacian matrix is known to have, for connected graphs, so in the case of not always, only one zero eigenvalue, exactly one zero eigenvalue, and all the others that are positive integers. Then basically by using an application of Kirchhoff's theorem, we can say that there are exactly these numbers, so the product of all the non-zero eigenvalues of the Laplacian, times the number of white vertices, number of perfect discrete Morse matchings on xi of D. Moreover, if we interpret the projection D as being the minimal diagram of an alternating knot, then the same expression can be written in this way, where the determinant of K is actually an invariant of the knot type rather than on the projection. And so we have the absolute value of the determinant times the number of black vertices times the number of white vertices. And this whole result is pretty straightforward once you have the previous generalization of Kauffman's clock theorem. But we can do a bit more. So we can also try to count non-perfect discrete Morse matchings, even though this is a bit more tricky. To do this, we use actually a symbolic version of the Laplacian, where all sort of the entries of the Laplacian matrix, if you know the definition, are replaced by symbolic versions. So basically the symbolic Laplacian is a matrix whose entries are polynomials with variables corresponding to the edges of the graph. So we can also consider the characteristic polynomial of the Laplacian, of the symbolic Laplacian, which we'll denote by this when we evaluate the sort of variable of the polynomial in -1. And then we can obtain the number of discrete Morse matchings on xi of D by considering this product. So we take the characteristic polynomial of the symbolic Laplacian evaluated in -1. We times this with the same thing on the white graph, and we look at this as living in this weird polynomial ring where again variables are edges in the black graph and in the white graph respectively, and where products of dual edges are 0. So we get a minimal representative of this product here, and then we evaluate all variables in 1. All the variables corresponding to edges in this product in 1. And this gives us the number of discrete Morse matchings. As a concrete example, we can consider the sort of simplest possible family of knot projections. These are the projections of the minimal diagram for the alternating torus knots with 2n+1 crossings. And in this case, it's it's not quite a straightforward computation, but one can obtain that there is precisely this number of discrete Morse matchings on xi of these diagrams, where these phi here are the Fibonacci number of the corresponding index here, while in a really more simple way we can obtain that among these exactly 2 times 2n+1 square are perfect discrete Morse matchings. Now we are going to look at a generalization of the second part of Kauffman's clock theorem. Basically, the second part stated that the clock graph is in fact connected. So the clock graph has vertices Kauffman states and as edges these clock moves. We are going to sort of extend the number of possible edges. We're going to pass from Kauffman states to perfect and admissible partial Kauffman states on a given Tait graph. And therefore, clock moves alone will not be sufficient anymore, and we have to introduce this new set of moves, which are called click path move and click loop move. And yeah, from now on, all matchings or partial Kauffman states, equivalently, that we're going to consider are going to be admissible. So, well, this admissibility in conjunction with perfect just means that each of these matchings will leave unmatched exactly two of the vertices in the Tait graph, and exactly one of these will be black and exactly one white. So let's see what a click path move is. We see, for example, on the black graph, we have maybe some portion of the black graph that looks like this, connecting this vertex VB prime to VB. This is a path of length 2. And here is the same picture on the Tait graph. So we have to add also the vertices corresponding to the crossings. Also, let's assume that we have a matching like this, which is alternatively matching half edges of G in this fashion. And let's assume also that this path is sort of maximal, meaning that this VB prime is indeed the unique black vertex which is unmatched by this red matching here. Then what we can do is simply grab these matched half edges and shift them, in this case on the left, by half edge. This has the net effect of matching VB prime and leaving VB unmatched. Then we can, if we have instead a loop, so assume that all of the red half edges here are part of a matching, we can do precisely the same thing and pass from the red ones to the green ones by shifting either clockwise or counterclockwise the red half edges. However, this does not change the position of any unmatched vertex, while the click path move does. So this is called the click loop move for clearer reason. So the first thing we can say about click path moves is that they induce bijections between perfect discrete Morse matchings on the reduced Tait graph for a fixed choice of forbidden regions, not necessarily adjacent. In this case, we're just talking about partial Kauffman states, and perfect discrete Morse matchings for another choice, any other choice of forbidden regions. Again, I want to remark that since we are talking about only admissible matchings here, one of these regions is black and one is white in both cases. Moreover, at most two such click path moves are needed to establish a bijection between any two sets of discrete Morse matchings. Using this, we can actually deduce what I mentioned before, so that the image of the Kenyon-Propp-Wilson correspondence, so the map from trees inside perfect matchings on the Tait graph, always consists of discrete Morse matchings. So recall that we had two different cases. One where the regions, the two, let's call them forbidden regions, were adjacent, and in that case we had a bijection, and those where we got an injection when the two regions were not adjacent. What we're claiming here is that in all cases, for any choice of forbidden regions, we still get a bijection with a set of discrete Morse matchings for which those two are the forbidden regions. So the correspondence here, in this case, goes both ways. Each discrete Morse matching, if it's perfect and admissible, comes as the image of some spanning tree from the KPW correspondence. Okay. now we're ready to state the proper generalized version of the second part of the of Kauffman's clock theorem, which is called Clickclock theorem, again for clear reasons. And this goes as follows. So if we start from a not projection which is reduced, and again, if you don't know what a not diagonal projection being reduced means, this is just a technical assumption, it's not really needed. But the intuitive idea is that D is not reduced if it's clearly the diagram connected sum of two smaller not diagrams. So if we start from a reduced diagram like this, then any two perfect and admissible matchings on its state graph will be related by a finite sequence of click path moves, click loop moves, and clock moves. So stated another way, if we consider the graph, the click-clock graph, whose vertices are these perfect admissible matchings on the Tait graph, and edges are either given by one of these three kind of moves, then this graph would be connected and would contain, of course, all the possible clock graphs that are obtained for different choices of forbidden regions, but even more. And the proof of this is surprisingly not straightforward, or at least we couldn't find any really direct route to prove this. And the proof we found is based on these two lemmas. So the first one is sort of easy. It states that two perfect and admissible matchings on this cellular structure on two sphere determined by the projection have the same Jordan resolution if and only if they are related by a finite sequence of click path and click loop moves. So no clock move involved. And the second lemma, which is the really tricky one, states instead that up to clock moves and click loop and path moves, so all possible moves that we have in our toolkit, we can make the Jordan trail of a perfect and admissible matching connected. So what does this mean? That if we start from any perfect and admissible matching on a given not projection, we can perform a suitable sequence of these moves in such a way that after a certain number of steps, we are always reducing the number of connected components in a Jordan trail, in the Jordan trail associated to that admissible matching. And I'll be more clear in just 1 second. Okay, so let me first say that given a perfect and admissible matching on the Tait graph, clock moves can have different sort of behaviors with respect to the number of connected components of the Jordan resolution. So either they leave this number unchanged or they change it by plus or minus 2. So we can divide indeed clock moves into 3 different types depending on the number of Jordan cycles that they involve. So in this case here, you see at the top, this clock move, we have 1 Jordan cycle here involved before and 1 after the move. In this case, to perform this move, we necessarily must have 2 cycles that sort of merge and split in such a way that after the move we still have 2 cycles, just a bit shifted. Instead, the moves we are interested in are this kind of type 3 clock moves, where performing the clock move, let's say from left to right, actually decreases by 2 the number of Jordan cycles. So the strategy for the proof of the second lemma here is to kick our partial Kauffman state with a sequence of click loop and click path moves until we get in a privileged sort of configuration in the diagram where in the Tait graph, where we are allowed to perform a type 3 clock move in this way, thus reducing the number of Jordan cycles and sort of applying this by induction until we get something connected, which is basically what we want for this second lemma. So let me go a bit through with the idea or ideas behind this proof. First of all, we can prove again a complete characterization of admissibility in terms of the number of components in the Jordan resolution. To be more precise, a perfect matching is admissible if and only if its associated Jordan resolution has an odd number of cycles. In particular, yeah, of course, 1 is odd, so we recover that trivially that all Kauffman states were admissible. Then, in a different direction, we can define another operation on graphs. Specifically, if we have a plane graph and a tree inside it, you can see here an example in red, we can define an operation which is called leaf spin, which basically just consists of taking a leaf, so a terminal edge here in red, and swinging it about its terminal vertex. So you can see here this edge here becomes this edge here, and again here we have spun this leaf clockwise instead, and from this one we get this one. The point of this is that if this tree was the let's say part of the induced subgraph of some matching on the Tait graph, we can prove that all of these leaf spin moves can actually be realized by applying a sequence of click path and clock moves to the partial Kauffman state that induced this. And that will come handy in just a few minutes. Then possibly the hardest part of this proof is to show that the induced black and white subgraphs of a given Kauffman state always behave as follows. So so first of all, let me note that, or let me say that these bluish circles here represent the connected components of Jordan resolution. And since we are starting from an admissible matching, we know that there is an odd number of such cycles. And what I claim is that the black and white graphs will be placed as follows. So if you consider this blackboard, this slide, as being compactified suitably to get S2, then at the center here we have a rooted white graph, rooted white tree induced by the admissible matching. Then this is surrounded by the first component of the Jordan resolution. Recall that all components of the Jordan resolution give us neighborhoods of the induced subgraphs. So this component here is surrounded in turn by this black subgraph, which is of a particular form. So it is basically just a cycle with a bunch of trees attached to it in this way. And this is called sometimes a pseudo tree. Again, then this is surrounded by another Jordan component. Then we have another white pseudo tree, and then finally, after an even number of pseudo trees alternating in color, we get in the external disk here just rooted black tree. So all perfect and admissible matchings induce in their black and white subgraphs respectively this sort of constellation of subgraphs, which are either, which have exactly one component which is a tree and whose all other components are pseudo trees. Then we can change the subject again and consider compactification of plane graphs. So if we have a plane graph whose sort of external part like this, it forms a circuit, a cycle, we can just compactify it all at infinity, obtaining another graph on S2, which has this privileged vertex here, which we call again a root. And if we started from a graph which had this sort of contained this sort of subgraph in bold here, which consists of the whole boundary of the plane graph, plus some tree attached to it, and another connected component disjoint from everything else in the middle here, then what we get here is an induced subgraph obtained by collapsing this external part. And yeah, sorry, I forgot to mention that this black part inside here should be an almost tree, meaning that it differs from a tree by just the removal of a single edge. So, for example, here you see if we add this edge, we get a tree, or this edge, or this edge, or basically any other. In this case, we get a tree, and this is called an almost tree. So once we have this, we can, given any plane graph, we can consider a further graph whose vertices are the set of almost trees inside G, and whose edges are given by leaf spins of these almost trees. So as I defined it before, leaf spins were only defined for trees, but it's easy to see what happens with almost trees. And yeah, this graph constructed from almost trees with leaf spins is in fact connected. And what this quite tricky result actually gives us is the existence of a certain really good configuration that we can choose at will, on which we can prove that we can actually apply the clock move of type 3 that I mentioned at the beginning of the proof, or better, this idea of the proof. And applying such a move will reduce by 2 the number of Jordan cycles, and so we can apply this construction inductively and obtain a connected Jordan resolution. And at that point, once we have a connected Jordan resolution, it just suffices to apply the usual clock theorem, and that completes the proof of the Clickclock theorem. Now, to conclude, I wanted to spend a few words on certain simplicial complexes that are associated naturally to can be associated naturally to matchings, as matchings on diagrams, for example, as we just saw. And the first one is the matching complex of a simplicial complex. Basically, we are just considering all possible matchings on the phase poset of a given simplicial complex. And it's not hard to see that this has the structure of a simplicial complex on its own, since if we remove any edge from matching, we still get a matching. And all the singletons belong to the simplicial complex. And we denote this for a simplicial complex X, we denote this by M of X. Here you can see an example with the cycle of length 3, so a graph, but seen as a simplicial complex, so a simplicial complex of dimension 1. In the special case of graphs, it's easy to see that the phase poset actually coincides with the first barycentric subdivision of the graph. And here in the center we get the matching complex associated to this. So for example, we can see this top simplex here is generated by 1, 0, 1, so this half edge here in the phase poset, then 2, 1, 2, and 0, 0, 2. So these three edges here form a matching that gives us this 2 simplex here, and the same for all other phase and phase sets here. Another thing that's well, another similar or related object that was introduced by Chari and Joswick around 2005 is the same thing, only for discrete Morse matchings instead of just matchings. And it's slightly more trickier to prove, but again, also the set of discrete Morse matchings on the phase poset of a given simplicial complex has the structure of a simplicial complex. And of course, since any matching is in particular a discrete Morse match, since every discrete Morse matching is in particular a matching, we get for free this inclusion as sub-complexes. In fact, much more is true, meaning that this discrete Morse matching complex is the starting point of a filtration that abuts to the matching complex. But I'll talk about this in another video. What one can do then is construct these simplicial complexes for a whole bunch of, well, not diagrams, not projections so far, and compute their homology. And here we have the examples up to 6 crossings, and where the notation here is as follows. So the exponent, of course, denotes the rank, while here in parentheses we get the homological dimension where these complexes are, where the homology is supported. So you can see that the actual computations and values that we get are quite varied. That does not seem to be a pattern. It would be quite interesting to associate to these homology classes some combinatorial or topological quantity that one can read from knot diagrams. But so far, I'm not sure that anyone obtained anything interesting. Let me conclude with a few, let's say, possible directions one could take from here. So the first one is look at this sort of filter complex that I just mentioned, from the set of discrete Morse matchings to all matchings, and look at the homology of the associated graded object, in particular in the case where we start from a knot projection, and see again if there's some connection to known invariance, which is also the main theme of the last sort of point here. Then, well, what were Kauffman states used for originally? Well, they were used by Kauffman to construct a state sum for the Alexander polynomial, which is something which came in handy also more recently with certain construction related to knot-Floer homology. So what one might want to do is to generalize a bit sort of this construction. Recall that Kauffman states are obtained as perfect admissible matchings with a set of fixed and adjacent forbidden regions. And what one does to obtain the Alexander polynomial is to associate a sort of bigrading to each Kauffman state and to each component of a Kauffman state, and then summing them all up somehow. So one might wonder what happens if, instead of considering just Kauffman states, we consider partial Kauffman states with non-adjacent regions, or partial Kauffman states that induce discrete Morse functions, and we have this sort of extra degree of freedom here. It would be interesting to see whether these Alexander polynomials do actually contain some meaningful information. Also, something else that could be done is to look at knot invariants that can be extracted from the stable homotopy type of these simplicial complexes. So this would amount to to define a decorated version of these simplicial complexes that keeps track of the over-under information of diagrams, and then to look at how Reidemeister moves change its homotopy type, and use this to define a sort of stable homotopy type of these matching complexes. And I think that someone is actually working on this last point at the moment. So I think I conclude here, and thanks for sticking around for so long, and see you next time.